So let me start with a very brief introduction of how these two fields interact between each other. I think there are three main genres here, how these fields interact. So first of all, when you think about quantum physics and computers, then what comes to your mind is quantum computers. And then, indeed, machine learning algorithms are sometimes adapted to be used on quantum computers, and then the time and memory complexity may scale completely differently than for respective algorithms on classical computers, and hence, in some scenarios, quantum algorithms might be faster. In some settings, classical algorithms might be faster. And then the second is application in a common way of solving physics problems. So very commonly, when you have a physical setup, then you try to guess its parameter-dependent state, so-called wave function, and then you minimize the energy of this system, just like any other function in machine learning. And it turns out that sometimes these wave functions can be inspired by machine learning. Like here is an example of pictorial representation of a wave function that is inspired by a restricted Boltzmann machine, a common generative model. And then it turns out that for some systems, such approaches outperform the commonly used wave functions previously in respective fields. And then the third one is using completely normal machine learning that we are used to in physics problems. And here, like in the previous talk, Adam talked a lot about dealing with large experimental data, or we can use it for optimal control of some experimental setups, or even generating ideas for new experiments. And I will be talking about our work in this subfield, you can use it for reconstruction of phase diagrams, which are central object of study in physics, and I will introduce them very shortly. So now, from this general introduction, I would like to move more into detail of our recent work, which is now available on arXiv and is in peer review. So it's about reconstructing phase diagrams. So let us first start with a brief overview of what phase diagrams are, and generally phases of matter. So phase of matter is like a state in which roughly matter can be. Like here we see, as an example, phases of water. Here is the solid water, also known as ice. Here is the liquid water, also known as water. And here is the water vapor. This is actually already liquid water, but it signals the presence of water vapor previously here. Of course, other substances can have more interesting phases, like helium is used in gas phase for helium balloons. But apart from a normal liquid phase that is pictured here, it has also a very interesting phase called superfluid, which is completely non-viscous, spreads, and has a bunch of other interesting properties. And then, studying of these phases is central to physics, and most commonly, they are studied in terms of so-called phase diagrams. So for water, let's say we know that the phase is dependent, obviously, on temperature, but also on pressure. So here you can see that for atmospheric pressure, which is this horizontal line here, obviously water freezes in 0 degrees Celsius and boils in 100 degrees Celsius. And such diagrams, which represent phases dependent on relevant parameters, are called phase diagrams. And here is the one for helium, just for comparison. And you can see, indeed, this superfluid, normal fluid, gas, and solid. And these diagrams are created for real substances like helium or water, but also for some more abstract constructs that are used to model relevant physical setups. So Let us now dive more into these abstract systems, namely spin systems. So you've heard probably that, for example, an electron has spin, which is like an additional degree of freedom of an electron. It is either pointing up, so-called spin 1/2, or pointing down, so-called spin -1/2. And then, like, a commonly studied scenario in physics is when you have several of these spins, which are placed near each other in some structure and interact between each other. Most likely, just nearest neighbors interact. Sometimes more of them interact. And then this can be used as an abstraction of some, let's say, crystals or any other materials that might come relevant. And then, of course, 1D is the simplest possible spin system, but this idea can be easily generalized to 2D, like rectangular lattice. And then in 2D, you can stack layers, and then you have like layered 2D models, which are also studied. For those of you who have some physics backgrounds, an example interaction can be just a sum over nearest neighbors and multiplication of the spin operators. And then, like these systems, also exhibit different phases. For example, they might exhibit different phases depending on how strong this coupling J is, or like how strong a coupling within a layer is, and how strong the coupling between the layers is. And then, like, various techniques are used to derive these properties. And then this brings us to the problem in our research. So we are given a two-dimensional phase diagram, just like these ones that we observed for water or helium. And we have two parameters, like one of them, J, is how strong the layers interact between each other, and K is how strong the interaction within each layer is. And based on that, we want to assign phases to points on discrete grids here. So we discretize both K and J, and then we have some finite set of points, and each of these points needs to be assigned to a correct phase. And then, obviously, we need some data to do that using machine learning. And it turns out that these spin systems can be simulated with old Monte Carlo techniques known for decades already. And we actually had a set of simulation data for these physical systems. And like for each point, for each pair of J and K, we had 600 samples. And they have shape 32 times 32, which means that this is a rectangular grid with 32 spins times 32 spins. And then it has two layers. And just to give you a visualization, here is an example. And like black can denote the spin pointing down, spin -1/2. White can denote the spin pointing up, the spin 1/2. And we not know even the number of phases that will be here. Like on the water phase diagram, we had 3 phases. On the helium phase diagram, we had 4 phases. We have no idea like how many we will have in our spin system. And we don't know like what will be relevant, whether to decide between the phase relevant will be whether they align or anti-align or like any other sort of parameter that can be relevant. We don't know that. Just based on these samples, also called snapshots, we want to assign phases to each of these points. And then, like looking at these snapshots, we see that they look almost like images, but of course not real photos, but it's still an image because it's a set of pixels on a rectangular grid. It's a very small picture, like 32 by 32. And also the depth of color is very small. We have just two possible values. It's binary data, and we have 2 layers, which can be thought of as something similar to 2 color channels. So like these 2 layers stacked can be a color image with 2 color channels. And then this brings us immediately to tools that are used to recognize images in like normal machine learning. And the most one, or at least one of the most successful tools to deal with image data in machine learning is the convolutional neural network. And here comes our idea of using it for this phase diagram reconstruction. So convolutional neural network have very good track record of solving tasks such as deciding whether an image is an image of a cat or a dog, or similar classification problems. So here we feed our network with snapshots for 2 different points of phase diagram. And our idea will be just to use this network to decide whether they are more likely to be in the same phase or in a different phase. And how we do it? We just feed with the network with these snapshots, and we attempt to train the network to distinguish them. And the rationale here is that if this training succeeds, it means that these 2 points should be in different phases because their snapshots are somewhat different, and the network can learn to distinguish between them. If this training completely fails, then it means that they are most likely in the same phase because the network just cannot distinguish between snapshots coming from these 2 points. So then we come up with something like, we call it quasi-distance between 2 points. And if phi is here the training accuracy, if this accuracy is perfect, like 1, then this distance is 1. If the training completely fails, which means that the accuracy should be around 50% or half, this quantity, this quasi-distance will be 0. Yes?
This is some type of multi-class classification class?
Or yes?
What type of task is this? Is it classification or?
This is binary classification task. So the task is to classify the phase given this snapshot.
How do you know the number of phases before?
So that's the idea. The idea is that we don't know the total number of phases in the phase diagram, but given 2 points of the phase diagram, we have at most 2 phases. Because we just have 2 points, and we want to see whether they are in the same phase or in a different phase. Just given 2 points, not the whole phase diagram, but 2 points of it. And then this is the idea. Like decide whether 2 points are most likely to be in one phase or 2 different phases. And then the detailed algorithm is that we divide these snapshots into 80% of training and 20% of validation. And this accuracy from the previous slide is the accuracy on validation set. And then, we scan through the whole phase diagram, through this whole J and K space, comparing pairs that lie at most 2 apart from each other. So for each pair of sufficiently nearby points, we perform training the neural network completely from scratch for each new pair. And we calculate this quasi-distance that I mentioned, which means how likely 2 points are in the same phase or how likely they are in different phases. And then based on this quasi-distance, we process this quasi-distance data a bit, calculating a value that we call Laplacian here. And high values of Laplacian, such as this in white or very light green here, means that in this region, points are different. So we are likely to observe a phase transition. While low values mean that we are in regions where phase transitions is less likely to happen. So with this sort of scanning window, we detect phase transitions here. And then we see that we have 2 phases here. From our physical intuition, we call one of them ordered and one of them are unordered. This is another example of results, some other physical system. And we observe similar behavior, like high values of Laplacian signal a transition between phases. And here we have no transitions, so we say that this is one phase, and this below is another phase, and some limiting cases can be calculated exactly, and we observe that this machine learning approach actually agrees with these exact calculations. And one important thing or interesting thing worth mentioning here is that sometimes the difference between two phases is really clear. So if you look at the difference between phase 1 and phase 2 for this system, we see that phase 1 simply has most of spins pointing up, while phase 2 has most of the spins pointing down, or at least, sorry, like half of them pointing down. But like we see very clearly, just looking at one layer, that they are very different. But if we look at the difference between phase 2 and phase 3, we see that the layers don't differ much. We just see noise. But if we multiply the layers, the difference becomes very clear. And the network has no idea that we need to multiply these two layers, but it still learns that there is a transition here. And then our goal in the future will be to dive more into this explainable artificial intelligence and kind of make the network not only distinguish between different phases, but also tell what is the relevant so-called order parameter. Here, we just knew that it's the product of two layers, but the network just learned to recognize it anyway. And then, towards the end of my talk, I would like to summarize that at first, I was talking about the general interplay of machine learning and quantum physics with three different ideas here, like using machine learning on a quantum computer, using machine learning as an inspiration for so-called variational wave functions, or just using normal machine learning for problems in physics research. Our work is about like finding phase diagram in completely unsupervised way for layered 2D spin systems. And the biggest challenge of it would be like not only recognizing phases, as I said, but also actually reconstructing what is the relevant quantity that distinguishes between these two phases. And the paper, the preprint, can be read on arXiv. And in the last minute, I think, of my talk, I would like just to thank my collaborators. So at IST Austria, where I am based, I collaborated mostly with Giacomo, who was responsible for preparing the snapshots for simulating these physical systems. And we also had 3 Italian collaborators that were responsible for the physics and for comparing our results to physics calculations using other techniques to see if they are wrong or right. And then I would like also to advertise IST Austria, where I'm based. This might be of interest, especially to students among you, but not only. This is a very young 10-year-old research institute. We have physics, mathematics, and computer science and life sciences. There is a PhD program, there are machine learning groups, and there are some successes already within these 10 years. Like it's us who have the highest success rate in European Research Council grants. And last but not least, we have a very green, beautiful, modern, and state-of-the-art campus. Thank you very much.